Good day, everyone. We're reviewing Wetzel's Limnology textbook, edition number 4, and we're on chapter 8, which deals with water movements. And we're in part 2, and right now we are looking at boundary layers. The concept of a boundary layer, the region where velocity gradients form due to friction, is critical for understanding flows in lakes and rivers. Boundary layers form wherever the flow is in contact with either the atmosphere or a substrate. Due to friction, a velocity gradient results in du over dz, and parcels of water are stretched. The eddies typical of turbulence results because of the spin imparted due to these spatial differences in velocity experienced by the parcels of water. Hence, boundary layers tend to be turbulent except in thin layers adjacent to the atmosphere and near a substrate. A boundary layer forms near the surface of water bodies where currents induced by wind decay as a function of depth. Similarly, boundary layers form in streams, rivers, and lakes as currents interact with the margins. Velocity u decreases from the surface downward or increases from a substrate upward in a region called the logarithmic layer, where so let's see here, in a region called the logarithmic layer, where law of the wall, LOW scaling, applies. Interesting. Where K is the von Karman's constant of approximately 0.41, and U star is the friction velocity, Z is the depth, and Z0 is the roughness parameter, which depends on, but is much smaller than, any distortion of the substrates, such as rocks of submerged plants on the stream bottom or surface waves. Friction velocities are thus equal to the slope of the line relating the logarithms of normalized depth, height, to flow speed. Measurements of U at two heights allow estimation of U star without consideration of Z0. Friction velocities are often distinguished with respect to the atmosphere U star A prime and to water U star W. So let's see here. So the first one, figure 8-6, we have a schematic of a stratified lake using boundary layer classification. The upper layer is the surface layer in contact with the atmosphere, also described as the actively mixing layer in chapter 7. And the lower water column adjacent to the sediment water interface is classified as the bottom or benthic boundary layer. Also included are the energy fluxes from incoming streams. So we have the energy fluxes, I believe, right here from inflows. We have the surface layer, the metalimnion and the hypolimnion. We have the center of mass and the center of volume. And let's see. So values black font are in watts per meter square. The kinetic energy in the surface layer is included Ekin, joules per meter square. So Ekin is the energy from the kinematic energy. So we have delta E here, Ekin is right here. The figure also illustrates that when a lake is stratified, the center of mass is below the center of volume, okay? So the center of mass is below the center of volume, with the distance between them being delta Hm, and work to overcome the resulting difference in potential energy delta EPOT is required to mix the lake, and for delta Hm to therefore be 0. So for mixing to occur, you have to have the center of volume and the center of mass being close to each other, and therefore you need to apply some work in order to decrease this delta Hm to 0. This concept underlies the calculation of the Schmidt stability and lake number. Changes in heat content over the summer, delta H heat, which is here, 10 to the 9, so that's a fair amount, as shown in white font, with in units in joules per meter squared. Inserts to the right illustrate the density line, so density increases with depth, and temperature structure. So the temperature structure, we have temperature X, no, that's actually, sorry, this is the stability. We have stability here, and then we have an increase in stability and decrease in stability, I believe. Let's see, in heat content, okay, inserts to the right, okay, so we got that. and temperature structure indicated by the color of the line yellow is warmer than blue. Okay, so I see. So this is like also temperature is kind of like baked in here. So we have like warmer temperature compared to colder temperature here. And insert okay, and so let's see. And those to the far right illustrate stability as obtained by differentiating the density profiles. The basis of the calculation of buoyancy frequency. Dissipation rates indicative to the extent of turbulence can be orders of magnitude higher in the surface layer and bending boundary layer than in the interior. Figure 8.7. Boundary layers are identified by changes in velocity with depth due to friction. Velocity u decreases due to friction on the bottom of a stream are apparent when plotted against normalized depth zd on a linear scale left panel. Here, depth z was normalized by dividing by the full depth d of the channel, except in a thin layer near the bottom, not shown. Changes in velocity occur as a logarithmic function of depth, yielding a straight line right panel. So this is the logarithmic base scale. This is the z over d, which is your normalized depth, and this is u, which is your velocity. So your velocity here increases with your increasing ZD in your normalized depth, and which is then the same curve, but now it's been applied to a logarithmic base scale. The slope of the line is called U star, where U star is known as the friction velocity. Flow within the logarithmic portion of the boundary layer is generally turbulent. The channel was 0.09 deep and 0.851 meters wide. In this study, except very close to the substrate, the full depth of the stream was a boundary layer. Okay. So let's see, we read over that. So let's move on to here. The thin layer adjacent to the interface, only micrometers thick near the air-water interface and millimeters thick on the bottom of lake, is comprised of the viscous sublayer with the diffusive sublayer within it. Here, the magnitude of turbulent diffusivity is less than kinematic viscosity, V, and of molecular diffusivity. The thickness of the viscous sublayer, sigma, is computed as sigma is equal to 11 V over U star W. Variation from law of the wall scaling occur when the water column is stratified or when vegetation is present, and at the air-water interface when surface waves are present. As will be discussed later, turbulence in boundary layers has many biological and biogeochemical implications, from circulating phytoplankton throughout the upper mixed layer and modifying their light climate to causing variation in annual succession in species composition and influencing redox profiles in the sediment. Mixing and dispersion. Flow in lakes and streams is primarily turbulent. These chaotic flows lead to the spreading or diffusion of the solutes and particles within them. Velocities u of a turbulent flow can be averaged to have a mean component of u bar and fluctuation u prime. The latter by definition would average to 0, so the product of the square of the fluctuations is computed, average over time, and then the square root taken, yielding the root mean square velocity. And u root mean square velocity is equal to, is less, so u prime 2 is greater, square is greater than 0.05 in the power. I'm not entirely sure what that means, but we'll probably find out. Where the angled bars indicate averaging. This calculation is one approach to obtain the turbulent velocity scale u defined earlier. Here the velocity u implicitly applies to all three directions of ocean. Transport by the mean flow is referred to as advection. The turbulent eddies, which have the velocity scale described above and an average eddy size L, cause turbulent diffusion K, quantified as proportional to the product of the turbulent velocity and length scales, that is, K is approximately URMS L. Spreading in the horizontal is more often quantified with a horizontal dispersion coefficient KH, and mixing in the vertical with a vertical eddy diffusivity, although the usage is not always consistent. Both have units of meters squared per second. Due to the challenges in quantifying turbulence, key concepts have been extended from the understanding of molecular flow. One is out of these is a concept of the Fickian diffusion, in which the flux F of mass of solutes per unit area per unit time is proportional to the gradient of concentration in the vertical direction, and for molecular diffusion D, the flux is F is equal to minus D dC over dZ, where C is a concentration over the length, and D is the diffusion flux, and F is your flux of mass of solute. Okay, so let's see, we have some more calculations here. So similar reasoning is true for the vertical flux of solutes. Thus, if eddy diffusivity coefficient and the concentration gradients of solutes are measured, the flux of the solutes due to the turbulence can be quantified. The reasoning behind equation 8-11 led to the heat budget approach for computing the coefficient of eddy diffusivity in lakes. In the next 4 sections, approaches for quantifying turbulence are provided, as well as brief summaries of the magnitude of dispersion and eddy diffusivity coefficients in streams, rivers, and lakes. Additionally, perspective on turbulence production and the use of KH and KZ will be provided in the context of the physical processes occurring in these water bodies, with description in sections 2 and 3 of this chapter. Tracer approaches to quantify dispersion and eddy diffusivity coefficient. Injection of a tracer such as colored dye or a gas that will not react with lake or stream water is frequently used to quantify dispersion. So this is an example of a confluence of the turbid light color Queen River on the right and the clear dark color King River on the left here in Tasmania, Australia. Dispersion and spreading of each tributary inflows are characterized by dispersion coefficient and the mean velocity U. So figure 8-8 and 8-9AD illustrate the spreading of tracers in the horizontal in a river and lakes, respectively, to obtain horizontal dispersion diffusivity coefficients. Figure 8-9E illustrates the expected spreading of a tracer injected at 22 meters in a 44 meters deep lake. Values of K are computed from the rate of change over time of the spreading. Horizontal dispersion coefficients have been found to scale with the size of the dye patch. The experiment illustrated in figure 8-9 confirmed that the relations between obtained in ocean water and in the Laurentian Great Lakes also apply to small lakes. The scaling K is equal to C1UL, where C1 is a coefficient to relate the contribution of turbulent eddies of different length scale and velocities U. Turbulence and its measurements. So turbulence is quantified as turbulent kinetic energy, take TKE per unit mass in joule. So let's see. So this is figure 8-9, dispersion of a central release of sodium fluorescein. So I'm assuming that, let's see, in a short release of rhodamine red dye into Twin West Lake on 24 August 1988. The central release was at 12:48 and the shore release at 12:59. So here we go. So we have like that rhodamine release, and then we have the central release of the fluorescein here in the middle, I believe. So let's see, the photographs were taken at 1310, so this is the first. So we just got this dye released, and B 1318, C 1325, and then D 1336. Spreading of tracer and E. Spreading of a tracer injected 20 meters above the bottom in a 45 meter deep lake. Here depth Z is positive upward from the lake bottom. So here we have lake bottom, and then we have probably the lake surface at 45 feet. The coefficient of eddy diffusivity Kz prime m meter square per second determines the vertical rate of spreading as indicated by the dashed lines, with first samplings having higher maximum concentration. With continued sampling, the tracer spreads even farther from the injection points. So the concentration increase here, right mid-level of the lake. And so first, like we're done with this, I mean, it shows basically that the dye is spreading out. from a central point, and I'm assuming that the central point is here. That's where they released it, but it's a little unclear. Definitely, this is the shoreline base, and then so we're then saying like after a while, so probably about a little less than an hour, we can start to see a disorganization of the plume of the dye. And here, what we are seeing an increasing in concentration. And as for the two different curves, they determine the vertical rate of spreading as indicated by the dashed lines, with first sampling having higher concentration. So this is probably first sampling here. With continued sampling would spread even further, and then we have decreasing concentration as the time elapses. Okay, I think let's move on to maybe 810. Ka, apparent horizontal diffusivity as it increases with patch size L based on data from the ocean and Laurentian Great Lakes. An apparent diffusivity is calculated from the rate of spread of the dye patch, and the word apparent takes into account inherent undersampling and other complexities when doing field work. So this is Lake Ontario, Twin West Lakes. This is your Ka and your L values. So accurately quantifying the coefficient of diffusivity requires calculating the flux Richardson number RF and the mixing efficiency gamma under steady state. RF is defined as, I will let you read that, is a convective flow. So gamma is a larger in convective flows in which cooling induces instabilities. Returning to the concept of energy cascade, to the kinetic energy per unit mass is proportional to the turbulent velocity scale squared u squared, and near boundaries is also approximated by u star squared, where u star is the friction velocity and the transfer of energy is proportional to u cube over L, where L approximates the size of the largest eddies in the flow. The analysis above then links the larger turbulent scale to the smaller scales, such that the dissipation rate can be estimated at sigma is equal to u cube divided by L. This relation indicates that the viscous decay of energy can be approximated by the large-scale dynamics that are independent of viscosity. In the following, we see how this approximation enables methods to compute coefficients of eddy diffusivity. Measurements of turbulence are usually based on quantifying its rate of production. Both approaches require instruments that can sample at frequencies high enough to enable measurements of the fluctuation in velocity. Quantifying turbulence production requires instruments that measure both velocity gradient and velocity fluctuations. Measurements of sigma have been obtained from multiple approaches. One approach takes advantage of the rate of transfer of turbulent kinetic energy to progressively smaller scale, that is the Kolmogorov minus 5 to the divided by third power law within a sub-range of wave numbers. Calculation can also be based on the distance over which turbulent motions are coherent, or with large eddy approaches. Fluxes of scalars, such as dissolved oxygen, can be obtained from the product of oxygen fluctuations and vertical velocity fluctuations, a procedure known as eddy covariance. Such fluxes can also be obtained with high-resolution profiles of oxygen near the sediment. Water interface combined with high-resolution velocity measurement, velocity and temperature gradient microstructure profilers enable the rate of dissipation of turbulent kinetic energy. The use of temperature gradient microstructure profilers was enabled by critical theoretical work that established the relation of small-scale temperature fluctuation to dissipation rates. The assumption that turbulence production is balanced by dissipation enabled Kz to be calculated for profiling data. Estimating Kz accurately requires accounting for the forcing mechanism and proximity to interfaces, turbulence in streams and rivers. Flow in streams is mostly turbulent, driven by the channel bed slope and modified by the stream morphology. Water is advected downstream, while shear at interfaces generates turbulence that rapidly removes any patchiness in concentration, and if strong enough, may also scour the channel and modify its shape. Velocity is near zero at the sediment water interface, and as illustrated in figure 8-7, increases logarithmically within the boundary or the bottom boundary layer, which is a maximum in the central channel, and then decreases just below the water surface due to shear at the air-water interface. As stream velocity decreases, turbulence may decrease. For bulk flow in streams and rivers, the horizontal dispersion at kh is in the order of 10 to the minus 2 to 10 to the 10 to the meter square per second. Velocity and turbulence are, however, not evenly distributed vertically or horizontally in streams. Benthic boundary layer provide shelter for macroinvertebrates in fast-moving streams or during spates when boundary layers form adjacent to cobbles and boulders. Flow in the near shore may be somewhat disconnected from the main stem flow, and associated turbulence, the quieter waters support the development of complex lateral habitat. Turbulence, so why don't we complex may proliferate, and organisms in associated food webs are not advected downstream or scoured from stream bed. So why don't we stop right here, and I'll see you tomorrow, and we'll go over turbulence in lakes and ponds. So stay tuned for our water movement chapter 8 of the Wetzel's Limnology textbook, and I'll see you soon. Thank you.